Hey everybody, welcome back to another video about calculus. So, in this video, we are going to be talking about implicit differentiation and related rates. You might be like, well, what is implicit differentiation? So far, what we've been doing is we've been working with explicit functions and their derivatives. So what is an explicit function? Maybe it's something like y is equal to 4x squared minus 7, or y is equal to 32x to the 6th minus 4 over square root of x plus 27. Something like that, right? Where we have our dependent variable, which could also be like f of x, as a function of the independent variable, and the dependent variable is all by itself. But it's really easy to construct equations that don't look like that. Maybe I have something like x squared y equals 1. And I still want to make sense of derivative in this context. Well, how do I make sense of derivative in that context? Well, this one, we can do something for it. We can rearrange it into explicit form pretty easily. So long as x is not equal to 0, this rearrangement is true. Okay, so that's good. That works. And now we can make sense of the derivative there. But what about more complicated implicit equations? Some implicit equations are so nasty that it's not worth or straight up impossible to get them into explicit form. Maybe you get hit by something like x times y to the 5th plus x squared y cubed minus 1 divided by the square root of x times y minus 5 is equal to 27. Nasty. I'm not even sure that I could get it into explicit form, even if you gave me like a day to do it. And I do this for a living. But what if your real-world situation that you're trying to model happens to have this as its describing equation? Well, you'd be SOL if you just wanted to work explicitly. But we don't have to. We have this tool called implicit differentiation that we're going to use to be able to solve things like this. Maybe not that one specifically. Let's do an example of it first and kind of build up what we're doing from there. Suppose y cubed is equal to x. And say we wanted to find dy dx. Okay. Think of a derivative now instead of like another function as an operation you can do. So what I'm going to do is I'm going to have this equal sign and I'm going to take the derivative on both sides. Right? If these two things are equal, their derivatives with respect to the same variable should be equal. So d dx, and yes, it's important that it's x. d dx of y cubed is equal to d dx of x. Okay, that's all good. Now, let's compute the derivatives on both sides. This side is easy. d dx of x is just 1. What about this side? Well, okay, I'm taking the derivative with respect to x, but there's no x's to be found. What is true, though, is we kind of have a chain rule going on behind the scenes. Y is a function of x, so you can think of it as like y of x. So d dx of y of x, or any function of y, right? d dx of y of x is what we want. d dx of a function of y, by the chain rule, is going to be equal to f prime of y times dy dx. And we want the dy dx, so that's good. Okay, applying that knowledge to here, by the chain rule, this derivative is 3y squared times dy dx. And that's exactly what I want. I want my dy dx. And I can get it by itself really quickly. Just divide both sides by 3y squared. 1 divided by 3y squared. And we say, that's done. You might be like, well, wouldn't I rather have the derivative as a function of x? Yes, you would. But to do that, oftentimes would require an explicit equation, which we've established you can't always get. So we're saying, okay, I'm content to leave it in terms of x's and y's for my derivative. And yeah, there's a whole branch of math called differential equations, which is devoted to studying and solving these. They get really difficult in general, but it's easy to find numerical solutions, which is good enough for most real-world applications. All right, let's move forwards. And write out the general process for implicit differentiation. That's such a long word. All right, to do implicit differentiation, let's just write out more generally what we did over here. We took our equation and we differentiated both sides with respect to our independent variable, in this case, x. It is important that you take the same derivative on both sides. I can't take d dx on this side and d dy on this side. It would give you wrong answers, right? Because you can't do, for instance, adding on one side and subtracting on the other. You gotta make sure you're doing the same thing to both sides. So, differentiate both sides with respect to your independent variable, which most often will be something like x or t for time. And then after that, you solve for dy dx algebraically in terms of x and y. So, oftentimes, that's not that bad of a process. Implicit differentiation is a powerful tool. Let's do a few more examples of it. All right. Let's let y to the fourth minus y squared plus x cubed minus 1 equal to 0. And our classic objective, let's find dy dx. All right, to find dy dx, I'm going to take the derivative with respect to x on both sides. And let's write out all the steps for this one so we can see. Sorry, I took a derivative there before even writing it down. Went too fast. All right, so d dx of the left-hand side is d dx of the right-hand side. It's often helpful if you, before taking your derivative, make sure the right-hand side of your equation is 0, so you can just subtract whatever is on that side over, because the derivative of 0 is always just 0. So having constants on the right-hand side is good. Expanding this side out a little bit, you get d dx y to the fourth minus d dx y squared plus d dx x cubed minus I guess I have to move that over after all. d dx of 1 equals 0. Alright, let's start taking these derivatives. Again, by the chain rule, this is going to be 4y cubed. So this is the derivative of our big function, right, with respect to y, plugging in y. And then you multiply by dy dx. Ditto here. So you'll have 2y dy dx. The kind of mental shortcut for these ones where you're differentiating with the y's is, hey, do it as if you were taking derivative with respect to y, and then multiply at the end by dy dx. Okay? d dx of x cubed, power rule, 3x squared. d dx of 1 is just 0. It's equals 0. Alright. So step 1 is done. We differentiate both sides with respect to x and we simplified. Now, what we need to do is solve for dy dx. Well, I see it in both of those terms. I'll just factor it out. You get that dy dx times 4y cubed minus 2y is equal to, subtracting 3x squared on both sides, negative 3x squared. Alright? That's all well and good. Now I can just divide both sides by this. Remember, dy dx is a quantity, so we're not taking the derivative of this thing. These two are being multiplied together. Alright, dy dx is now negative 3x squared divided by 4y squared cubed minus 2y. And we say that's our answer. And if you manage to find a solution for y, then you'd have an explicit formula for dy dx as well. Let's do another example. Implicit differentiation is really powerful, not only because it allows us to solve nasty equations, but because it allows us to actually extend the idea of differentiation to something that isn't even a function. So for instance, let x squared plus y squared equal 9. So this is a nice and useful equation. This is the equation for a circle. Centered at the origin. With radius 3. Alright, so undeniably something that we want to be able to work with, and if you just look at it graphically, when we talk about derivative and we originally introduced it, it was an idea for solving slope of tangent lines. It still makes sense to talk about the slope of a tangent line here. So I still want to be able to do that, even though this is not a function, right? This is not the graph of a function, doesn't pass the vertical line test. Implicit differentiation is our way of saying, yes, you can still talk about the derivative and have it make sense. So that's nice. Let's find dy dx and an equation for the line tangent to the circle at the point square root of 6 square root of 3. So square root of 6 square root of 3 is a point that's on the circle. I think it'd be like here-ish, roughly. And we're saying, hey, I want to find an equation, not just the slope. I want to find an actual equation for this line. Well, okay, to find an equation for the line, the slope is kind of an important part. That'll be given to us by dy dx, plugged in properly. Let's do it. Alright, so to find dy dx, we're going to take the derivative of both sides. Okay? Derivative of x squared plus y squared will be 2x plus 2y dy dx, right? Making sure to apply that general. d dx of a constant, 0. Cool. And now it's really simple to solve for dy dx. 2y dy dx equals negative 2x. dy dx is negative x divided by y. The 2's cancel. Alright, so that's part 1 of our endeavor completed. Now to find the equation for the tangent line of the circle. Well, okay, I can find the slope by plugging in the proper coordinates. I have an xy pair. My slope depends on both x and y, but I know the x and y, as I said. So, dy dx evaluated at the point square root of 6, square root of 3. This notation here just means evaluated at is equal to negative square root of 6 divided by square root of 3. Based off our laws of radicals, that is negative square root of 2. Which kind of makes sense, right? It's a negative slope, bigger than 1, or negative 1. Alright, so that's our slope, but we need one more piece of information to find a line, right? You need either 2 points on the line, or a slope and a point. We have a point on the line, right? We know it hits the circle there, and we have our slope, so we have enough to find our line. Line's equation is going to be by point-slope form, which hopefully you remember from a pre-calculus class. Y minus y1, which is the point on there, the y coordinate that you know is on there. So y minus square root of 3 is equal to our slope times x minus the x coordinate you know is on there. Alright, that's a valid equation for it. I like to simplify it down into y equals mx plus v form. You get y would equal negative square root of 2 times x, right? Not square root of 2x, just square root of 2 times x. Let's see here. We are going to have plus square root of 12 minus square root of 3. But the square root of 12 is 2 times the square root of 3. So we're just left with y equals negative square root of 2 times x plus the square root of 3. And that is our equation for the line tangent to the circle at this. There will almost certainly be a question like this on your midterm, just FYI. Yeah. And we can also do more examples together as a class when we meet on Thursday. So let us move forwards. Where did my paper go? Ah, there it is. We can also talk about higher order derivatives that we find implicitly. And it requires no additional theory, just practice. Let's let x squared times y minus 3y to the fourth equal 1. And let's say we wanted to find the second derivative of y with respect to x. d2y dx squared. Alright, well to find the second derivative, we should probably find the first derivative. We do that by taking the derivative of both sides. That should be x squared times y minus 3y to the fourth is equal to d dx of 1. Alright, let's compute those derivatives. Here we have a product rule. So let's actually split that. We have d dx of x squared y minus 3 times d dx of y to the fourth is equal to d dx of 1. Alright, here we have a product of two things, x squared and y. So we apply the product rule. We get that this will be the first one times the derivative of the second plus the second one times the derivative of the first. And then let's leave everything else alone for now. Okay, we can now compute everything we need. X squared times d dx of y, well, d dx of y is literally dy dx. So we have x squared dy dx plus y times 2x we'll get. So 2xy minus 4 times 3 is 12, so we're going to have 12y cubed. d dx of 1 is just 0. Alright, let's get that first derivative by itself. dy dx times x squared. Sorry, I missed a dy dx there. How foolish of me. Messing up my own calculus class. Alright, so making sure to apply the chain rule, we get 12y cubed dy dx for that term. Now, let's simplify. Factoring out the dy dx from all the terms that have it, we get dy dx times x squared minus 12y cubed is equal to negative 2xy. Which therefore tells us that dy dx is equal to negative 2xy divided by x squared minus 12y cubed. And you ask yourself, okay, that's all well and good. Now how do I go from here to finding the second derivative? Well, the second derivative is merely the derivative with respect to x of the first derivative. So we just use our implicit differentiation technique once more. Okay, computing this derivative, unfortunately, this is going to be a kind of nasty one. We have a quotient, so we're going to use the quotient rule. And let's remember, quotient rule is bottom times derivative of the top minus the top times the derivative of the bottom, which I will put in there with an arrow, all divided by the bottom squared. Okay? Unfortunately, the trouble doesn't stop here. We have another product rule. So we're going to get x squared minus 12y cubed times, okay, let's break it up as negative 2x times y. We'll have first times derivative of the second, so dy dx, plus the second times the derivative of the first. So that'll give us minus 2y. Minus 2xy is plus 2xy times the derivative of this thing here, right? Derivative of that, which which will give us 2x minus 12 times 3 is 36, y squared dy dx. Alright, all still divided by x squared minus 12y cubed. Nasty, long, and complicated. Let's start simplifying it a bit. I went to all the work of writing it out for myself, but then I find myself just doing it again here. Maybe I should actually use my notes. Alright. Oh, I almost forgot. There's a negative. Oh, I put it in there. Cool. See, that's why I wrote it slightly differently on my notes, so I guess it's a good thing I was doing it myself the whole time. I just put the minus sign down there in my notes instead of up top. But we kept track of it here and here, so we're all good. Okay, let's do some simplification. Enough rambling on my part. We want to get the dy dx's as much as we can all together. So let's get the dy dx term by itself. You might be like, well, why do I still have the first derivative term if I'm trying to find the second derivative? We'll get there. We're going to have dy dx times. Okay, I'm going to have a negative 2x squared in there. And then we're also going to have the 36y squared times 2xy, aka 72xy cubed. So those are all the terms with dy dx's, and then all the rest can just do what they want. I don't care about them. We're going to have oh, sorry, there's also this term. Distributive property hits. We're going to have a positive 24xy cubed. And that should be a negative 72. Okay. So we have negative 72 plus 24, which will be negative 48 xy cubed. Right? Yes, negative 2 times negative 12, positive 24 xy cubed dy dx. There we go. So we're going to have dy dx times negative 2x squared minus 48 xy cubed. And then what other terms do we have? Distributing, we have a minus 2x squared y. We have a plus 24y to the fourth. Then over here, we have one more term left. We have the 2xy times the 2x, which will be plus 4x squared y. And actually, those terms are the same, so let's merge them. We get a plus 2x squared y at the end of that whole shebang. And that is all divided by x squared minus 12y cubed squared. Okay, so where do we go from here? I don't like the fact that there's dy dx in that equation. How do I get rid of it? Conveniently, we already have a formula for dy dx in terms of just x and y, so let's plug it in. This is equal to negative 2xy divided by x squared minus 12y cubed times negative 2x squared minus 48xy cubed plus 2x squared y plus 24y to the fourth, all divided by x squared minus 12y cubed, all squared. Let me check my calculations and then I'll be back in a second. Yep, we're all good. I'm proud of myself. This is our second derivative. The only thing you could really do is simplify this further without a bunch of work. Distribute this negative sign. They all become positive. That's about it. Yeah. This is something I would not expect you to simplify, because I wouldn't want to simplify it myself, and I'm never going to ask you to do something that I don't think I could do within a reasonable amount of time. So, yeah. That's that for that example. I wrote something down wrong. That's okay. Alright, let's move on to our next topic, which is that related rates thing. So, what is a related rate, and why do we care about it? Related rates are actually some of the most useful applications of the calculus. Well, what are they? Remember how when we were developing the chain rule, we were like, okay, I want how y changes with respect to x, and it makes sense that that would be the product of how y changes with respect to u and how u changes with respect to x. We expected this kind of multiplicative structure. And related rates are going to take advantage of that to give us information about physical systems. And when I say physical systems, I mean anything that's not just abstract math. Business, biology, chemistry, physics, you name it, you can do related rates problems with it. So, what are they? Say we have an implicit equation where both x and y depend on a third variable. Maybe call it t for time. That's the most classic thing to do. Say we know dx dt. Maybe I know what one of my variables is doing with respect to time. But what if I want the other? How do we get it? Right? Because if we want just dy dt by itself, we might say, well, okay, get dy dx, and that is, by definition, equal to, well, dy dt times dt dx. Once you know x dt, you can kind of backsolve for dt dx. It's not 1 divided by. But my point is, a chain rule is not going to work for us here. At least not without some work first. But we can make that happen. So again, let's start it off with an example, and then we'll build up the general process from there. Maybe a local one. Suppose the quantity demanded daily of Firestone tri-tip sandwiches is related to the price of the sandwich, which we'll call P, by a simple equation. P plus x squared is equal to 256. Okay? That's all well and good information for us. What do we actually want to figure out? How fast is the quantity demanded changing quantity demanded daily, I guess. When P is equal to 8 and yes, P is equal to 8 and the quantity, or sorry, the price per day is increasing by, so P is $8 and the price is going to be increasing by $0.20, 20 cents. Okay, so that's a reasonable question to ask, right? How much is the demand for my product changing when the price is at a certain amount and going up by this amount? If such a situation were to occur, what would my quantity demand do? Well, to answer that question, we use implicit differentiation. What we're looking for, or I guess what we want, is dx dt when what? What are we given for this? Well, we're given price is $8 and dp dt, price changing with respect to time, is positive 20 cents, right? The reason I say positive, if this were decreasing, we'd put negative 20 cents, because it's increasing, we put positive. So, price is $8, it's changing at a rate of 20 cents, and we want dx dt. Okay, how do we actually get that? Well, we have an equation right there. We know how to do implicit differentiation. Let's try something with that and see how it goes. Here, I want my derivative with respect to time. So let's take ddt on both sides. ddt of p plus x squared is equal to ddt of 256. E derivative of constant is 0. Okay? ddt of p is just dp dt. ddt of x squared, remember, since we're taking with respect to t, it's going to give us 2x times dx dt. So exactly the thing we want. But it's in terms of these other things. Well, okay, solving for dx dt gives us dx dt equals dp dt divided by 2x, negative dp dt divided by 2x. But, okay, I'm given dp dt, but not x. How do I get x? We have an equation relating p and x. So, let's use this equation to to solve for x. How do we solve for x? Well, we need p. We're given p. We know that x squared plus 8 is equal to 256. X squared is equal to 248. Which means that x is equal to the square root of 248, aka 2 times the square root of 62. You might say, okay, what about that plus or minus? You spent 12 years drilling into my head that the square root of something is plus or minus. Well, let's make sense of what we're doing here. We're trying to find a quantity demanded. It doesn't make sense to have a negative quantity demanded. So we're going to always take the positive root in this situation. Well, that's our x. We have all the other information we need. This is negative 0.2 divided by 4 times the square root of 62. Done. Since this is a more applied class, I'll put a decimal. This would be about 0.00635, and it should be dimensionless. I guess it would just be sandwiches per day. So, this is negative. Negative 0.00635. Okay, so the amount of sandwiches demanded is going down by 0.00635 sandwiches. I don't think Firestone's hurting too bad for that in this scenario. All right, let us move forwards and do more examples. So this is the kind of process we go through to solve related rates problems. You take the derivative on both sides with respect to the independent variable, and then solve using the information that you have. I see in my lecture notes I wrote that out formally. I'll write it out so you can too. To solve related rates problems. You're going to assign to each variable you're going to assign to each quantity a variable. So maybe price is P, right? Or if you're working with like a problem with a circle, maybe radius is R, so on and so forth. This step, it might be useful to draw pictures. Because sometimes the equations are given to you, right? Where we have the p plus x squared equals 256. But other times, the information, these kind of relationships come geometrically. So maybe you're working with a circle or a triangle, right? And then the picture can be really helpful. So if you're working with a physical quantity, draw a picture. Probably will save a lot of heartache in the long run. Second, you're going to write out two things. All given information and what you want to find. And write it out in terms of the variables from step 1. Third, you're going to write down equations relating the variables together. You might have one equation, you might have more. That's all the work you really need to do. You're just going to now take the derivative and solve for everything that you want. Derivatives are your magic tool in this course. When in doubt, take a derivative. So, differentiate with respect to the proper variable, which will most often be t, but could be other things depending on your choice of variables. Then the most blunt step 5, solve. Let's do an example. Say an oil tanker crashed. And the polluted area is expanding rapidly. Okay? Say the area that we're polluted, for the sake of simplicity, is a circle. In reality, obviously the oil would spread out unevenly, but for the sake of you being able to do this problem, any of us being able to do this problem, we'll say it's a circle. And we want to determine how fast, so anytime you see the word how fast, you think, okay, derivative with respect to time. How fast the area is increasing. When the radius of the circle is 60 feet and increasing at the rate of half a foot per second. So, very fast growing oil spill right there. And let's think about, does this problem make sense? Well, yes, if the area of a circle is growing, the circle's getting bigger, meaning its radius is growing, we're given the information about how the radius is growing and what stage of growth the radius is at. Now we're going to go and solve for how fast the area is going. This is our perfect tool for that. I'm going to erase that side, so make sure you get it down. Alright, step 1, let's assign our variables proper names and draw any pictures that might be helpful. Here, we got a circle, so I probably should draw a picture. It's probably helpful. Okay, and I'll just label my variables on there. We got our tanker in the center of the circle. Maybe the area of the circle is just A, that's our polluted area. Okay? Yeah, you can't really see that on camera. Okay? So that's our polluted area for the circle. And then our radius, we'll just call R. Okay, well we have our picture. I think we've labeled all of our quantities. Yeah, all the really important ones, right? T is equal to time. let's solve the problem. We're going to establish all the relationships we have with our variables and see what information do we have. Well, we know that in this situation, the radius is 60 feet. And we also know that the radius is increasing at the rate of half foot per second. In math terms, that means dr dt equals 1/2 feet per second. I have a bad habit of dropping the units as I go through a problem. It works out for me because I don't do physics. But it can be a helpful thing to check if something's going wrong. You're like, okay, what are my units through all of this? If they don't cancel out properly to give me like a reasonable answer at the end, then I might have done something wrong at some point. Okay, so we know that the radius is 60 feet. We know that it's changing at the rate of half foot per second. What else do we know about this situation? Let's take some information that we're given by this circle. I know that for any circle, area is pi times the radius squared. And that's important information since I'm looking for how fast the area is changing with respect to time, and I know something about how the radius is changing with respect to time. Now I have a relationship between area and radius. That's enough for me to start solving. So I want dA dt at this moment in time. Let's find it. dA dt is the same as the derivative of this side with respect to t. d dt of pi r squared, which will be 2 pi r dr dt. Nice. Well, I have dr dt, I have r, so in this case, dA dt is equal to 2 pi times 60 times 1/2. That'll give you 60 pi. And it would be in units of feet squared per second at this time. You could solve for what time it is, but actually I don't think you could in this situation. But at this point in time, where we have our information about the radius, we now know how the area is growing. All right, that's all well and good. Let's do more examples. Okay. Let's say that the demand equation for a set of headphones is 100 x squared plus 5p squared is equal to 3600. Alright, they gave us an equation, so thankfully we probably won't have to draw a picture, which is good because I wouldn't know how to draw a picture for that. Where x represents the number in thousands of headphones demanded each week. When the unit price is P. Alright, so we've already got a pretty nice setup here. We have an equation. We know that our variables x stand for quantity demanded and for unit price. Okay? And we ask ourselves the question, how fast is the quantity demanded increasing when p is equal to 20 and the price is dropping at the rate of 15 cents per headphone per week. So, reasonable question, right? Laws of supply and demand say price goes down, demand goes up. How much is the demand going up if the price is this much and decreasing a certain amount? All right. So, let's write out our givens and our desired. As soon as I pick this up off the floor. Our givens, well, I know P is 20. I know that the rate of the price is decreasing at 15 cents per headphone per week. So, dp dt is equal to negative 0.15. Do I know anything else? I still know this, right? That whole thing. Okay. Well, what do I want? I want dx dt at that instant. Okay? Well, let's go and get it. Take the derivative on both sides of this. That tells us dt of 100x squared plus 5p squared is ddt of 3600. That's 0. This is going to be 100 times 2x dx dt. So we're going to have 200x dx dt from this first term, right? Applying the chain rule. Plus, we're going to have 10p dp dt from the second term. Again, applying the chain rule. All right, I want dx dt, so let's get it all by itself. 200x dx dt is equal to negative 10p dp dt dx dt is negative 10 divided by 200 is 1 divided by 20. So we're going to have negative p dp dt over 20x. All right, that's dx dt, and it's depending on p, dp dt, and x. We know p, we know dp dt. I still need to find that x. So let's do it. Alright, I realized I erased that equation that gave us the whole thing. It was 100x squared plus 5p squared equals 3600. Okay, I need X. I have P. Let's find it. I know that 100 X squared plus 5 times 20 squared is 3,600. That tells us that, let's see, that's 400. So 100x squared plus 2,000 is equal to 3,600. 100x squared is equal to 1,600. X squared is 16. So x is equal to 4. Because again, if we're working with quantity demanded, it doesn't make sense for x to be negative, so we take the positive square root. And now, plugging all that information in, dx dt is merely negative 20, that's our price, times dp dt, which is negative 0.15, divided by 20 times 4. So in other words, positive 0.15 divided by 80. If you wanted to compute that with a calculator or something, it would give you, in fact, an equal 0.0375. Alright, and we ask ourselves, does this answer make sense? Yes. Here's why. We are having a small decrease in the price, right? Relative to the original price, this is a pretty small decrease. So we're getting a small increase in demand. If I got a negative answer somewhere here, I would know that I dropped a negative sign somewhere, right? Since when price goes down, demand should go up. And I should, under most circumstances, get a small number for changing the quantity of demand if I get a small number for change in price, right? Elasticity of demand. It would take a very elastic good for a small change in price to mean a large change in quantity demanded. All right, let's do another example. And then I think we will be good to go for this. Okay, say we have another demand function for a DVD player this time. And the demand function is going to be P is equal to negative 0.2 x squared minus 2x plus 160, where P is unit price, and X is quantity demanded in hundreds. Alrighty, well, what is going to happen here? We are going to compute the elasticity of demand for this good. And determine whether the demand is elastic, inelastic, or unitary. At x is equal to 15. quantity demanded is 1500, right? Then what is the elasticity of demand right there? And let's remember, elastic means that elasticity is greater than 1. Inelastic is when it's less than 1, and unitary is when it is equal to 1. All right. Should also probably write down the formula for elasticity of demand once more. Formula for elasticity of demand is E of P is equal to negative P times F prime of P over F of P, where X is equal to F of P. Alright, so not quite a related rates problem, but it's going to use similar techniques. I want E of P. To get it, I need this F prime of P, I need an F of P, and I need P. Okay, let us do it. Oh, also, this whole thing is screwed. We're computing the elasticity of demand at X is equal to 15. It would take more work to do it in general. We could do it, but it would be more work than I want to do. We can do it in class or in our example time if you guys really want. Okay, let's find this whole thing. I need P. I have X. Well, I have a relationship between P and X. So at X is equal to 15, P is equal to negative 0.2 times 15 squared minus 2 times 15 plus 160, which is 85. All right, so we're at a price of $85. Excuse me. We know that F of P, in this case, is X, which is 15. We still need F prime of P, in this case, right? Again, technically we're plugging in at P of 85, since we're working at a specific demand. Okay, let's find F prime of P. How do we get there? Well, I have a relationship between P and X. Let's find it out. Okay. F prime of P, by definition, if F of P is X, F prime of P is dx dt. How do we get dx dp? Using this relationship up there. We'll differentiate both sides of the equation with respect to P. I'll erase that side because I want to leave this stuff up, so get that down if you don't have it already. All right. We take the derivative with respect to P on both sides, and we get that dp of P is dp of negative 0.2x squared minus 2x plus 160. dp of P is just 1. That's equal to negative 0.4x dx dp. Right? Because that's what we're going for. We're going for F prime of P. Minus 2 dx dp. Plus 160 will go to 0 under the derivative. Okay. You might be like, why are we trying to find dx dp? Again, because F of P is equal to X. And what we really wanted is F prime of P. That just happens to be dx dp by our set. Alright, so that's all equal to 1. Factoring. 1 is equal to dx dp times negative 0.4x minus 2, 1 over negative 0.4 x minus 2 is equal to dx dp. So at x equals 15, f prime of p is equal to dx dp at x equals 15. Just plug in 50, or not 50, 15 into there, and you get, I didn't write it down. Negative 1 divided by, it would be negative, sorry, it's 1 divided by negative 6 minus 2, which is negative 1/8. Alright, so let's plug it in. E of 85, right? Because p equals 85 at x equals 15 is, by our formula, negative 85 times 1/8 divided by 15. Alright, so that's our elasticity there. Let me compute that real quick and then I'll be right back. Alright, so after a quick use of a calculator, because unfortunately I don't have you all in here to just be like, hey, one of you put this on your phone's calculator, which is what I would normally do. We get that E of 85 is 0.7083 repeating. Also, this should be a negative 1/8. Have it here, didn't write it down. Alright, so that's our elasticity. And the second part of the question was that inelastic, elastic, or unitary? This is less than 1, so this is inelastic. Alright, and I think that's that for that example. As always, feel free to shoot me an email if you have any questions, or we can discuss it in class on Thursday. Have a good rest of your day.